All right, we are going to continue our discussion of energy by talking about rotational energy. So I have what looks to be not a great drawing of a merry-go-round. So imagine a little kid standing here riding on the merry-go-round, if you will. So when you push the merry-go-round, you're applying a force to it, and the thing spins around. Now, if we look at this, zoom in here on the top view of our merry-go-round. If we look at this, as we apply this force to this spot, the thing spins, and we get our angular displacement. And the force does actually accomplish some work, and we know that work is force times our change in displacement. And the problem with moving in a circle is that if we continue to push this thing, as we go all the way around, the work that we do is going to be zero because we didn't actually make it, go anywhere. Even though we did put work into it, if we look at it as we go all the way around, we are making it do something. We are making it spin. So the way that we're going to talk about this is that force put energy into the merry-go-round, but the center of mass is not moving. And that says something very important. That says that the kinetic energy, or the translational kinetic energy, that's usually 1/2 mv squared, is zero. Because the center of mass isn't moving, there's no velocity to that part of the system, and so it doesn't have any translational kinetic energy. What we do have is an object that's spinning. So an object that spins has rotational kinetic energy. So yes, we put work into our system. It's not traditional work. It's a different kind of work. And we get a different kind of energy because of that. So rotational kinetic energy is 1/2 I omega squared. So if we look over at this thing, at our merry-go-round. So if we look at our merry-go-round, each little tiny piece of mass does have an instantaneous velocity at some point. And if we took and added up all the tiny pieces of mass and looked at all of their velocities in relation to the radius of everything, we get something. We'd end up with this expression for rotational kinetic energy. You can look in the book to see that actual derivation. I don't think it's worth our time. So this gives us another kind of energy to look for. So when we're looking at our total energy equation for any system, it's going to be gravitational potential, spring potential, translational kinetic energy, and rotational kinetic energy. These are now all of the possibilities that we have. We're going to have translational kinetic energy anytime the center of mass of an object moves. At the same time, gravitational potential energy is also for the center of mass of an object. Spring Obviously, if you have a spring, you have spring potential. And then rotational kinetic energy is for spinning. If something spins, we're going to consider rotational kinetic energy that go along with it. So, gravitational potential energy is for the center of mass. Translational kinetic energy is for the center of mass. Rotational kinetic energy is for something spinning. So we're going to look at two really quick examples of that. I'm going to make you hate inclined planes even more, if that's possible. So here we have an inclined plane of angle theta. Actually, that doesn't matter so much. So as we look at this, we can say that we have a height h, and just to be fun, let's say we have a solid sphere. Of mass m and radius r. So what we're going to do is release that thing down the plane, and we're going to look at what happens. So at the top, our energy is all potential. At the bottom, this thing is going to roll down. We're going to say that this has friction, which means we're going to have no slipping at all. So as this thing makes it to the bottom, it's going to be moving with a speed. At the same time, it's going to be rotating with some omega. So the energy here at the bottom is going to be k translational plus k rotational. Let me rewrite that. So the energy here at the bottom is translational kinetic energy, because we do have a velocity, plus rotational kinetic energy, because the thing is spinning. So let's look at how we're going to do this problem. Now, it's conservation of energy, so we can say that the energy at the top is equal to the energy at the bottom. So m times g times that h is my energy at the top. Energy at the bottom is 1/2 mv squared plus 1/2 I omega squared. Now, for that term, we know a couple of things. One, since we're not slipping, omega is equal to v over r, so that's going to, well, capital case r. Omega is v over r. We're going to plug that in. We also know that because we have a sphere, I is equal to 2/5 mr squared. Both of those things we can put in for this expression for our kinetic energy. So mgh is equal to 1/2 mv squared plus 1/2, let's plug in for I, so 2/5 mr squared, and we're going to plug in for omega, v over r. That quantity is squared. Now, because that quantity is squared, my r's can go away. And so this thing simplifies a little bit into something that we can work with. So mgh is equal to 1/2 mv squared plus, what is that going to be? These 2's go away. So 1/5 mv squared. 1/2 mv squared plus 1/5 mv squared. So mgh is equal to 1/2 plus 1/5. Let's see, is 7/10 mv squared. My m's go away. My velocity is the square root of 10/7 gh. So what I'd like to do is right next to this, right alongside of this, let's do the pretend case. What if there was no rotation? So that's a question. So if there was no rotation, it'd be mgh is equal to half mv squared. And my velocity would be the square root of 2gh. With rotation, we're talking about a little bit less velocity. So if we compare those two, we have less translational speed with rotation. Now, what this means is that our energy went to two places. It splits between translational energy and rotational energy. Nope, got off. It splits between translational energy and kinetic energy. It's not all going into the translational velocity. Some of that energy was spent, if you will, making the thing spin. This is a fairly simple example. We're going to spend some time doing these in class tomorrow, and here's a little bit more complicated of an example. So we're going to pretend that we have, just to make life easy for everybody, a uniform rod on a pivot. Okay, so we have a rod of length L, mass M, like that. Okay, we're going to drop it. So what we want to know is how fast is the end moving at the bottom. So when we drop this rod, we are 1, 2, 3, 4, 5, 6, 7, 8, 9.5. So when we drop the rod, it's going to fall down like this. I know that's kind of light to see, and it's going to be moving with some velocity. And what we want to do is figure out what that velocity is. So we have two different times to consider. The first one here is at the top. Now that's the center of mass of our rod. So the potential energy at the top is going to be mg times h, and we're going to figure that h out in a second. Now the next time that we have is down here at the bottom, and we need to think about what kind of energy the entire rod has. In this case, yes, the center of mass is moving, but if I wanted to take the translational kinetic energy, I'd have to look, since each one of these little bits has a different speed, I'd have to look at each one of those little bits and get its kinetic energy in order to figure out how fast this thing was going. So I'm not really interested in translational kinetic energy at this point. I am, however, interested in rotational kinetic energy. I have a rod that's rotating. I know what to do with that. So I got 1/2 I omega squared for the energy at the bottom. So if we, sorry about that, if we look up here at the rod and what it's doing, the center of mass, of this thing drops from the top down to here. In fact, our change in height is L over 2. So we've got is U equals mg times L over 2. That's the height that the center of mass dropped. Our potential energy, if we remember, is always going to be for the center of mass of our object. If you want a justification for that, think of that rod. This end of the rod is going to fall this far. And it's going to have a lot of potential energy change. Whereas this part of the rod actually doesn't fall anywhere at all, and it has zero potential energy. That's why we consider this center of mass. It's sort of the average for the entire thing. So again, potential energy is going to be for the center of mass of the rod. Now, in this case, we know that I is equal to, because it's a rod about its end, 1/3 ml squared. So at this point, we can sort of solve for what the angular velocity of everything is. We know that mg L over 2 is going to be equal to 1/2 times 1/3 ml squared times omega squared. So we know the m goes away, the 1/2 goes away, and one of my L's goes away. So, what do we have? Omega is equal to the square root of 3g over L. So, every bit of that rod is moving with that same angular speed. If I want to know the velocity, of the end of the rod, I know that the end of the rod, the velocity is equal to r times omega. At the end of the rod, my r is equal to L, and my omega is the square root of 3g over L. So the velocity comes out to be the square root of 3gl. These are some simple things. Obviously, this is going to get a little bit more complicated, and we're going to start throwing in all kinds of stuff to deal with this. In fact, we're going to do one of my favorite, potentially your least favorite problems concerning this in class on Monday. But the nice thing is I'm going